Hello, everybody. It's time to get started. Welcome to the session titled Leverage R and Spark in Azure HDInsight for Scalable Machine Learning. I'm Maxim Lukyanov, Program Manager in Big Data team in Microsoft. I work primarily on R Server and Spark as part of Azure HDInsight service.
And my name is Bill Jacobs. I am a Principal Product Marketing Manager. Was previously the Field CTO and VP of Product Marketing for Revolution Analytics, which produced the R products that are now Microsoft R Server and Microsoft SQL R Services.
Thank you.
Okay, so to get us going here, just for fun, I'm the marketing guy. He really knows what he's talking about, so I get to ask the fun questions. It's always interesting when we go into these audiences to have kind of an idea of where you guys are coming from and what you know and what you do. So let me ask a few questions, show of hands. How many of you can spell R? Great. How many can spell Python? Ooh, bunch of good students here. Second question, how many of you are primarily IT infrastructure professionals? How many of you would describe yourselves as data scientists? A couple of you, 3 or 4. I told you we'd get more here. Yep. Level 300 does it every time. How many of you are essentially application developers? All of you. Who did I miss? What job styles? What do you do for a living? Does a little bit of everything. Okay? Jack of all trades. Well, I'll have to ask that next time. The reason we ask the question is that the topic of R and Spark is one that is becoming incredibly important for a lot of large industries and down even into medium business. Spark's being used across the waterfront, if you will, in banks, in credit card companies, in healthcare providers, in drug research companies, in manufacturing shops where they're pulling data off of 10,000 chips at once on 20 wafers in a tray. And as such, it is providing not only a great opportunity to accelerate R-based data science, but as you'll see later in the session we're going to present, it is providing several different ways to do traditional statistics, machine learning, and deep learning using the various available toolkits that come with Spark. And Maxim is going to take you through a number of those. So with that, the only remaining question is anyone here an R programmer? Anybody here using R? Oh, quite a few, actually, half a dozen of you. Any Python programmers? We'll be nice to you guys, too. You're supposed to know better. But interesting. So we do have a pretty mixed crowd, which is kind of interesting. Again, my background is actually as an infrastructure guy who found his way into data science after a number of postings at companies like Sybase on their large columnar databases, which were primarily the engine of big data, along with some time I spent at Netezza and Greenplum. Maxim has a very different background, which I'll let him explain, but he's actually had the honor of starting his own company and doing some fun stuff. So why don't you tell a bit about your background?
Thank you. So I started as a mobile software developer. We had our little company, and then I moved to Microsoft and started working on fun stuff, which is big data, and then upgraded myself into even more fun stuff, which is machine learning on big data. So that's the topic of today's talk. And just to keep things moving, so we are going to talk about big data and scalable machine learning, particularly about R Server and Spark. And there are many things we can talk about these particular two products, so we'll focus on actually how those two combine combine with each other and actually allow you to implement a variety of machine learning tasks, whether you're R person or Python person, or even if you want to use something else entirely and dive into a deep learning topic. So we will talk about how we can tap into the ecosystem that is formed around R and Python and Spark projects and bring in the libraries that you need to accomplish what you want to try. And as an example of that, we'll use deep learning library. So how many of you have actually interest in deep learning? A few of you. OK, so then we'll keep it on the agenda. We'll try to talk a few things about what it is and then how you can use it as part of the product that we're describing here. So first, to give you context of what we are going to talk about, we are going to talk about scalable machine learning services in Azure. And we use Cortana Intelligence Suite as a way to describe a set of services available in Azure for solving big data and machine learning problems. And there are still many of them out there. So what we are talking specifically about in our context is a service called HDInsight. So that's the one that allows you to create clusters of machine to solve machine learning at scale on the clusters of machine, distributed machine learning tasks. So one comment here is that Cortana Intelligence Suite is a set of services. So you can acquire the whole thing. You can buy a Cortana Intelligence Suite. But it's important to note that you can also acquire the services, cloud services, on a as-you-need-it basis. So you can use HDInsight or any other services listed here as you need. OK, so let's dive into HDInsight. So we limited our focus into scalable machine learning. But even with that kind of limitation, there are still many things, I would say infinite world of possibilities in machine learning. So how do we describe all of those things that we can do with R server and Spark in our world? So we have a few data scientists in the audience, so you'd probably be ready to describe this classical categorization of machine learning algorithms, like reinforced learning, different ways to classify things, supervised learning, unsupervised learning, things like that. So academic way of categorizing machine learning algorithms. So in this case, we actually will take a different approach, and we'll categorize machine learning algorithms from the point of view of the business user, or of the users who actually pay for these algorithms or use them in their industry. So from that point of view, we have identified three categories. The first one is the traditional algorithms. And traditional algorithms is an algorithm that are most commonly used across a variety of industries and verticals. And these are well-known algorithms. We are primarily talking about predictive statistics here, hypothesis testing, some clustering, and common techniques like that. Specialized algorithms are less frequently used, but they have established themselves as a de facto way to solve a particular problem in a particular industry or vertical again. So a good example here would be a PageRank, collaborative filtering, PCA, and things like that. And finally, we have categorized deep learning algorithms into its own category, because this is a new thing that emerged in recent years that defines its own world of possibilities. It is a set of algorithms that now redefine what is possible with machine learning, and not only machine learning, but in artificial intelligence at large. So that's why we are going to talk about it as a separate category. So now that we have our categories defined, we can talk about use cases. So how these categories of algorithms are used, and again, all of those things are possible to do with R server and Spark. So for traditional algorithms, by definition, we are talking about a variety of use cases. And we will find them, as Bill mentioned, in a variety of industries. And we are talking about very established industries, like brick-and-mortar institutions that we know very well, like financial institutions and things like that. Those people, those industries, were doing machine learning for decades. And now they want to do it at scale and do them better than ever before. A quick example, we are talking about Acturian, who is calculating some risks in a financial industry and trying to determine what would be the appropriate rate of loan and things like that. So that's a very big industry, or set of industries that is addressed by the scalable machine learning products. In terms of specialized algorithms, we now go from the set of traditional industries into a world, in a more modern world of web enterprises. Good examples here, variety of recommendations engines. If you go to Amazon.com, it will recommend a product to you. And there are many other retail and other web properties that all do product recommendations. So those algorithms are well known and frequently customized. And a variety of similar industries like ad placement and predictive maintenance tasks are all being developed within this category. And finally, deep learning is a burgeoning industry now. It has a large number of startups that attempt to solve new problems in new ways. And as well established industries that are trying to solve problems in new ways and solve problems that we thought before were not possible to solve. In the Azure HDInsight service, those scalable algorithms are available as part of two products. The first one is the R server, and the second is the Spark cluster type. So R server is basically a Spark cluster type plus all of the R server capabilities on top of it. So we are going to talk in this session specifically about those two products and how they complement each other.
All right, and what I'm going to do here to kind of set the stage is to make sure we're all on the same page as to what R server is and isn't, how it works, and what it does. How many of you are familiar with SQL Server R services? A few of you seen that? Okay. It has a different name only because it is a particular version of the R server product. The R server product came to be when Revolution Analytics had recognized that R had some limitations with respect to memory, with respect to single-threadedness, and with respect to local-only execution. We set about fixing those things about 5 years ago and grew the capability for a subset of the algorithms to actually implicitly exploit parallelism and remote execution and do so in a way that was machine independent. In other words, if I build my engine to break a big problem into many little problems and I run them serially, I can run them on a single-threaded CPU. If I take those same algorithms and run them in another substrate that understands distribution across multiple threads, let's say a big Windows server or a Linux server, it's the same problem for the guy who's writing the code. He says, call the algorithm. The algorithm says, break the problem up into many small tasks and hand a tenth of them to each thread until you get your work done, combine the results, cycle back if you must, iterate in some algorithms, but in the end, return one result for the user. So we built a family of highly scalable, memory independent. In other words, we call them out of memory, meaning that the system doesn't run out of memory, but it can run on data that's far larger than memory. And we completed that work so that we could leverage simply very large servers with lots of threads. And then along came a little elephant called Hadoop and presented an opportunity for yet another degree of utilizing that very same infrastructure, which is take the task, break the task into lots of little pieces, take each little piece, figure out which node's got the data that piece needs to eat, marry them together, and run that in MapReduce. As a consequence of embracing the Hadoop engine in MapReduce 1.0 and a very similar instantiation we did for Teradata EDWs, our company grew in 3 successive years from 2 million to 8 million to 20 with essentially no increase in headcount. And that demonstrated to us that there was an exploding market opportunity to build massively scalable capabilities that made that power accessible directly from simple statistics-oriented languages like like R. One-letter languages really messed me up. Like R, I can spell them both as a marketing guy. And emergently, we're seeing similar activities in Python. We'll be embracing those, and some of what Maxim will show you is both. So let's walk through the R server a little bit. I did this slide a while back because I realized that a lot of people were saying, yeah, I know about R, and they thought about the language. Frankly, it's a decent language. It's kind of old. Anybody here old enough to have programmed in Fortran? Good. I feel so together with you guys. That doesn't happen very often. It is of the same vintage as, say, Fortran and Pascal in its origins, but its focus as a language is dead center on the things that statisticians need to do. Anybody ever write loops in R? You get caught doing that, the other R programmers say, why are you doing that? R is designed to eliminate that kind of thing. It's designed to make it very easy for statisticians to manipulate two-dimensional tabular arrays of data to do things like correlation analyses. What's a correlation analysis? It's a matrix conversion. Easy calculation unless you have to do loops, and it's like lots of code. In R, it's one line. So that's what R is. But the key thing is it's not the language that's important. It's great that it does things statisticians want to do. What's cool about R is the number of people that have adopted it as their secondary or primary language for various attributes of data science. Anybody here actually call yourself a data scientist? A couple of you. Do you really have another title, like statistician?
Officially, that's it, yeah.
Okay, yeah. People argue whether data science needs to be a title or not, because sometimes people only say data scientist because they read the latest article that said, here's how you add $20,000 to your salary. We get that. But the burgeoning community around the world, the last time we tried to count it up or project it from the number of user groups and the number of attendees, we guessed around 2.5 million people, and we think it's far higher than that now. Taught in most universities. I'm from Colorado. I live in Denver. Married a Colorado University grad from the business school. Guess what they teach in the MBA program at CU? They teach R. I found that a little bit shocking. We're beginning to see business professionals trained with the basics of prediction using the R language as a new tool for business. And that's creating a solution to a huge problem in data science, which is that hiring these people is hard. If you're really a data scientist, you really understand R and stats, I bet you get job offers pretty regularly.
I just got one about an hour ago.
Send it my way. I'm going to tell them not to contact you again. The problem is a huge labor pool problem for most CIOs. And R is a solution to that because the universities are cranking out large numbers of R programmers. But probably the most interesting piece of R is the biggest result. Over the last 15 years of the use of R, the community has learned to share their work. The comprehensive R archive network, which that slide's a little different than mine, the 8,000 contributed packages are one repository, and it's called the Comprehensive R Archive Network. You'll hear it referred to as CRAN. Our programmers share their work. There's probably 150 versions of linear regression in CRAN, right? And data connectors to gene sequencing machines, and file formats that no one thinks about very much. But the cool thing here is that R is a language, but the value of R is the community and the shared work that you can get for free. So much so that, and I've continued to watch these numbers rise, and I remain surprised. I just picked this up off of the IEEE site just a week ago. We watched R jump from number 9 in the rankings in 2014 to number 6 as the most popular single function language. And in 2016, it actually bumped C# down. This is because there are so many people from outside the computer science world that are using R to do statistics, much like accountants like my wife learned to use Excel to get around having to hire a programmer. And so this exploding growth doesn't look like it's going to abate anytime soon, and R is being chased by Python for many of the same reasons with more of a computer science focus. That's why we're kind of foundationing this talk on how do you use Spark as a place to host R and Python and other types of data science. So Microsoft R, looking at this point of view, simply provided a way to address memory limits by acting on data block at a time, performance limits by recompiling algorithms in C++, scale problems by leveraging many machines and clusters, and finally, the ease of use problem of big shared clusters by permitting remote execution. And you'll see all of this expressed in what Maxim is going to show you. But the key thing that results from it is not only can we tackle really big problems in a language that wasn't really designed originally for really big problems, but we can do so in a way that leverages the power of running inside of a database or inside of a Hadoop cluster where data does not get picked up and hoisted over the network and duplicated. And in some of the cases we've seen, 80% of the performance burden today's data scientists are dealing with is because that's how long it takes to shovel the data out of the EDW over to the compute server. And oh, by the way, we do the compute faster as well, but oftentimes the data movement is the biggest piece. For about 80 functions in the R server product, we have created versions of those algorithms and functions that are designed for parallelism. They're rewritten in C++, and they are prepended by a head-end that knows how to ship the work over to another system remotely. And what you'll find is a lot of very typical load and test data for profiling, test data for quality and distribution, and then a series of algorithms in the middle for predictive statistics that are the typical statistical functions followed by actual variable reduction, clustering, and other techniques that are commonly used in data science. Each of these runs on a whole bunch of platforms exactly the same way, whether it's a Windows PC, a Teradata EDW, a SQL server, or a Spark cluster. So the other thing that we do is we maintain full compatibility with open source R, because remember, those 8,000 shared algorithms out there as well, and nobody wants to give those up. We've talked about the scalable functions. What we also provide are 3 frameworks to allow you to build your own function. If you want to build a function that does a transformation on all the rows in a data set and uses all the nodes of a Spark cluster to do that, we have a framework called that. It's called RX Data Step. And so not only do we parallelize about 80 functions, but you can do your own. And so with that, I'm going to show you a couple of bits here about how easy it is to go from open source R to Microsoft R, because it is actually based on open source R. But fundamentally, when we read data in R, we basically say, go read from a CSV file sitting out at a URL and put it in a data frame. This my data variable is actually a 2-dimensional structure called a data frame. And then we can directly, in R, in a single line of code, run something like a generalized linear model, a GLM, on that data set and produce an object that contains a predictive model in 2 lines of code. Now, it's never really that easy. It's 3, sometimes 4, or 400 if you have to transform a lot. But that's how easy R is. When we want to run an R server, we're now contemplating really big data that's living off in another system. We want to push the work to the data instead of bringing the data to the work. We establish a connection to the remote system, a definition of that system in a connection object. And we pull the data across the wire by switching to a remote executing data function called RX text data. And then we run a version of logistic regression, which doesn't run locally. It runs on the selected data in the remote, called RX logit, for remote executing logit, which is logistic regression. So very simple changes to the code. The remaining changes, if we have 3 or 4 Spark clusters, a Teradata warehouse, and a SQL server sitting out on our LAN, we need to define which of those remote systems we're going to push the work to. And we do that with a set compute context. And there are 4 or 5 of these functions that set context. They say run in Spark, run in SQL Server, run in Hadoop, MapReduce, run in Teradata. So very simple changes to the code. And that gives us the ability then, and this is probably the most important slide about the R server product that you would take away. We support all the platforms listed. We support them all the same way. This gives you 2 things you can do. 3 things, actually. You can write a script that acts on a tiny sample of data until you know that script runs really well on your workstation, and immediately promote that script to run on, say, a 10% sample of the data instead of 1%, and run it in a bigger server to validate your algorithm. So you can start small and go big without changing any code. The second thing you can do, and the one that many data science shops find so useful, is you can do your modeling in one platform and take the predictive object, the model object, and run it in another system. What that means is you can move your modeling to your data lake if you build it in the cloud or in a Hadoop cluster, and still bring those models home to run in your Linux, Windows, and SQL Server boxes. This allows you to go to the cloud a little bit at a time, a huge transition enabler. And finally, we've followed the industry into Hadoop, Hadoop MapReduce Yarn, Hadoop MapReduce, Hadoop Yarn, and now Yarn Spark. You can bet we will follow the next step of the industry as well. So we're abstracting your data science work or your data science team's work away from the platform so that they are not disrupted the next time IT says, Spark was wonderful last year, it sucks now. We're going to go to system XYZ because it's 10 times faster. So we abstract those two activities away to reduce the disruption. So I'll skip past some of this because I think the things that Maxim wants to tell you are probably a little bit more important. But when we're running in Spark, we are a native Spark task. We are invoked by a copy of our server that runs on an edge node in the cluster. The HDInsight platform automatically deploys all of this for you. And when you request from a workstation, there's the data, there's the algorithm, go run it. It invokes a Spark cluster, passes the work off into the Spark executors, which is how Spark works. And inside each Spark executor, we process all the blocks of the data, just as we would on any other platform under the R server umbrella. Because of that, we can sit directly beside any other Spark task acting on those same data sets. The examples Maxim is going to show you are both R and Jupyter-based. Jupyter is the notebooking tool that we use for things like Python, and there are Jupyter R notebooks as well, allowing many people to work on different parts of a data flow, different parts of a problem. One guy does loading and feature selection, another guy is a model expert, third guy knows how to deploy it to make it run in production, and do all that with a mix and match tool strategy where all the tools fit together naturally in Spark. And that, to me, is the greatest advantage of Spark. It's a fast product, linearly scaled out to 2.2 terabytes of data in this particular example on a 100-node cluster, and didn't seem to show any kind of tendency to knee over. And this is how the product was designed. This was chewing on the airline data set, which is airline arrivals. Not only do we scale linearly with cluster size, but we can scale out essentially to the limit of Spark clusters, gated by things like the ability of the nodes to ingest data from storage. Way faster than running locally. When we run on big files, even compared to local big servers, we get big boosts in performance. The 7x boost I'm showing here is the effect of moving from open source to the C++ algorithms that we built. And the 36x is how much faster it was in some tests we did running data locally when we were able to spread it out over the nodes. So this is what you get from our server, whether you're running it in Spark or SQL Server or on a big Linux or Windows platform. But what Maxim is now going to talk to you about is how you can combine that power for your R programming population with the work of your other programming populations who may want to use other features of Spark, either from R or from languages like Python or perhaps Scala and Java. So with that, I'm going to turn it over to Maxim to talk a little bit about Apache Spark. Thanks.
Thank you. Yeah, so R is awesome, and now it runs on Spark, and Spark is here to stay. It's not going away next year. But anyways, maybe it will.
It'll just get better.
But Spark, at least as of last year, Spark actually showed the ability to release new releases, release new features with the releases very frequently. It was about every 3 months that a new minor version of Spark was released in the past year, and it included important features with it. And now we're even talking about Spark 2.0 that was released maybe that took a little longer than 3 months to release that, but it actually offers new performance enhancements and new takes on the architecture of Spark. So Spark has great community, fast release cadence, and it's gaining more and more traction in the industry. Like if you were at Strata conference last year, then Spark at that moment in time was big news. So lots of sessions about Spark. Everybody was talking about it as a big news. But this year's Strata conference, Spark is no longer big news, but it's a big part of every product, or almost every product out there in the big data industry. Every large vendor of Spark, of Hadoop now supports Spark. And if you go to a show floor, like we have here at Expo, at the Strata, you'll see that startups and companies bigger than that, they all have a Spark strategy. So Spark is a great new platform. One of the things that attracts people to Spark is its approach to big data as a separation of the framework into a platform piece and a workload piece that work on top of it. So that makes it distinct from the Hadoop in the past, because if you're familiar with Hadoop, if you worked with it, if you didn't use R server that isolates you from the Hadoop world, if you actually worked with the Hadoop world, then you know that in Hadoop there are many projects, they're all great, but they all look different. If you worked with Hive, that's one world. If you worked with Peak, which is an ETL tool in Hadoop, then it will look completely different. You need to learn new language. If you wanted to use machine learning tools from Hadoop, which is delivered by Mahout library, then it would be completely separate world. So Hadoop was great, but it was a kind of a mishmash of different projects put together to solve some specific problems. Spark takes it to a next level, where it provides very nice high-level abstractions for all of the workloads to integrate nicely with each other and to build on top of this common computation engine that Spark provides. So in that regard, you can see that Spark SQL, Spark Streaming, which is a real-time solution from Spark to process real-time events, GraphX, and machine learning libraries are all nicely reusing the same core framework of Spark. And if you're familiar with core Spark, then you'll find similar things in all of these frameworks. They all work with the same syntax, they all use the same concepts, and they all can connect to the same data sources that Spark can connect to. In that regard, when we ported our server to work on top of Spark, we took benefit of all of these Spark benefits as well. So now our server uses, in the Spark mode, can use all of the data sources that Spark can connect to. And it looks exactly like any other workload from the computation engine point of view. So if you were to debug Spark jobs that run our server jobs, you would find yourself in a familiar world if you're familiar with Spark platform. But one question that arises here, and we get it frequently from our customers, is, hey, Spark has machine learning library, and our server is all about machine learning. So which one do I choose? There seems to be a conflict between the two. So in this session, we wanted to answer that question and compare the two together and see what the difference are. So if you look at the Spark machine learning algorithms, this is the list. And it looks actually fairly similar to the list that our server has, because this list represents basically a traditional machine learning algorithms that are used everywhere and are very common. If you compare our server and Spark in terms of algorithm coverage, we'll get this picture. So you'll see that there are a lot of green checkboxes that say that it's the same algorithm implemented in two platforms, and there are a few exceptions. But the situation changes completely if you look at the language-specific view of this table. Spark is not a single language platform. It actually supports R, Python, and Scala together with Java. So if you look at that from that angle of view, then Spark R actually has very few algorithms available for machine learning. And with Spark 2.0, the situation is improving. They're adding new algorithms, but the coverage still is very lacking. So immediately at this point, you can start to differentiate that the world of machine learning, even in the world of Spark and R, is a very different thing when you take into account the language. If you look from the Python language point of view, then Spark machine learning libraries look great, because Python is one of the preferred languages in Spark world, and it has very good set of bindings for all of the algorithms that are available here. So what this combination tells us? Well, that you can get R language from our server, and that you can get Python language from Spark machine learning library. I found one survey that I'm showing you from KNuggets website that focused on the data scientists community and measured popularity of languages across data scientists. And if you're a data scientist, probably that's not a big news to you, but these numbers confirm that across data scientists, there are actually two languages that are most popular: Python and R. So with that, we can say that with our server and Spark, we have great coverage for all of the needs that you might have in your data scientist team. If you have R people, well, it would be hard probably to teach them to move to Python, and vice versa. So the language is a matter of, it's a fact. You have to just provide tools in the appropriate language to the people that you have. And with our server on Spark, you actually have a unique opportunity where the clusters and all of the actual manifestations of the tools that you create actually can support both of those at the same time and achieve fruitful collaboration between people regardless of their preference for language, whether it's R or Python. Also, there's the combination of the R server and Spark itself allows us to have better performance for the R server itself. That's great. And other capabilities of Spark combined with the R server capabilities are also very useful. And we are talking here about data exploration tools that are very rich and powerful in Spark ecosystem. And then you can combine those with the data visualization tools that are also rich and powerful in our ecosystem, and use the best set of tools that you need for your job. Okay, let's take a look at the demo. So let's switch. Perfect. So in this demo, we'll try to simulate the scenario of, hey, how would you use Spark and R together? So we'll start with this airline data set that we all love. It's our favorite. And we'll start with a problem statement where we say, hey, I just got new data set. It's massive. It's hard to manage. So how I can go and be productive about first learning about this data set, exploring what it contains, then transforming it into something that I can use for building my models, and finally actually building these models. So we have put this data into data lake, so that solves a set of problems by itself. And in the Jupyter notebook, how many of you are familiar with notebooks first? Just a few. OK, so let's talk a little bit about notebooks. So Jupyter Notebook is a Python project that actually, I think, was one of the first ones that introduced the concept of the notebook. And the notebook is a fairly simple thing. You can see in this one, I have some description. And that description says that, hey, then this next cell here will load data. So that's the idea of the notebook. You can combine descriptions and pictures with the cells that actually contain code. And that helps you describe what you're trying to do and actually do these things at the same time. You might think that, oh, that's a logical approach to the problem, but trust me, before notebooks, we actually didn't have that. And with notebooks, it gives us this very powerful tool that combines visualizations, descriptions, and actual code. So what I did here is I referenced this data set in the data lake and looked at the beginning of this data set using Spark Python commands. So now I can see that this data set has something with curly braces in the beginning, and I have I have enough reason to guess that this is probably a JSON document. And if you were following how long this cell execution took, it took just a few seconds. So that allows me to be productive about exploring this data set. And to give you ideas, this data set is actually about 100 gigabytes in size. It contains 160 million of rows. So you can be productive with big data set in Spark, or explore it interactively. So that's great. So now, as a next step, I can use built-in capabilities of Spark to infer schema and understand schema of the JSON documents. And this is a little snippet of code that not only reads this data, but converts it into a table. And this conversion happens as a schema, at the schema on read principle. So with this statement, I'm just telling Spark, hey, look at this JSON document and create a schema of the table that would describe this document. But don't do anything with data. Just create the schema, and then I'll use the schema as a lens to look at the JSON document as a table. So once I have executed this and I pre-executed this cell, it takes a few seconds, I'll get a table called flight. And from this moment on, I can use actually regular SQL commands. And in Python, in Jupyter Notebook, we have built-in support for SQL, for Spark SQL, to start querying and working with this table. And an important intermediate step here that I took is to cache. Now that we have table, I can cache this table in memory of my cluster. That would speed up subsequent steps, as you will see. So now that I have this cached table, I can start working with it to explore what it contains. So first, just counting all of the rows, we can confirm that without removal of all of the noise from the table, it has 160 million rows. And as one of the examples of exploring what it contains, I can build a table or chart that shows me an average arrival delay based on the day of the week. So if we look at it, Let's switch day of the week, put it on X and delay on Y. That should give us the chart. Let's switch to area. So one of the tools that we have on our Azure HDInsight clusters as part of this Jupyter notebooks is this widget that automatically visualizes the results of the SQL query. So that allows me to be productive in my kind of understanding data steps. So now we can see that arrival delay depends on the day of the week in the following manner. And I didn't decode the days of the week. One corresponds to a Monday and 6 to a Saturday. So on Saturday, arrival delay is much lower, about 3 minutes versus 8 minutes on Friday. So assuming that now I have gained some understanding of my data, I can move on to prepare the data for modeling task. So this task that transforms data is something that it would be actually harder to do in plain R, but is very easy to do in Spark and Python. So we won't execute this step, but our idea of data preparation or data cleansing step would look something like I will select the columns that I want and save the data in some new place. So now I can use this cleaned up data for my modeling step. And to do this modeling, let's use now R. And there are many tools that you can use for R development, and one of the popular ones is RStudio. So here we have RStudio server installed on the HDInsight cluster. And that gives us this IDE-like environment directly in the browser. And that's a very popular tool out there. Any of you working with RStudio? Oh, actually, quite a few. Awesome. So in RStudio, we have installed it on the edge node, the same node that we have our server working on. And it's pre-configured with all of the connection strings and with all of the stuff that you need to actually run your R program. So now we can directly address our data in our data lake, use Rx HDFS file system command to specify a read operation for the data. And then we can start building some decoding operations for our factors, for some columns in the table. And the important piece here is instructing our server to actually use Spark compute context to distribute computation on our Spark cluster. So let's execute that part of the code. And once this completes, we can actually launch a distributed Spark job that would build a linear model. And that would be just a simple linear model that calculates dependency of the arrival delay on the day of the week. That's kind of a fancy way to compute average. So now we can see that it's doing something. And if we switch to our cluster resource management UI, so we use Yarn as a resource manager, and Spark is integrated with Yarn as well. So here we can see what resources which jobs use. And now you can notice that there is a new job, new application, a new Yarn application created called Spark R that started using full resources of our cluster. So we have 10 nodes in this cluster. This is D14 VMs, very powerful ones. And on demand, our algorithm from R, transparently for us from the R point of view, created this distributed Spark job, and that started executing. It should take about a minute for it to complete. Oops, and I pressed F5 in the wrong place. Interesting, what will happen? OK, let's give it a chance to recover. Stop script. OK, let's continue. Oh, it's recovered. And you see, RStudio working on our server cluster is very robust. It even survives F5. And you can see that it's finishing this Spark job. So we can see Yarn application disappearing here. So now it finished the model building step, and it released the resources back to the cluster. So you can run any other Yarn application or Spark application to use these resources. That's great. Now what we get, what we got is a model. Let's scroll back here. Yeah, so we can use regular Spark, regular R server functions to look at this model, see its summary, and use our charting mechanisms to plot results. So let's plot it. You can see that the results that we get are actually comparable to the results we got in a previous step in the Jupyter notebook, that on Friday, the arrival delay is greatest, around 9 minutes, and on Saturday, it's lowest, around 3.7 minutes. So that confirms that the two produce similar results. We can also use the counts feature of the model to see how many data points were for each bin. And you can see that on Saturday, number of flights were actually much lower than Friday. And that can give us hints of why Saturday arrival delays are smaller. So to conclude that part of the demo, we can build a simple, which model we use here? Regression model, logistic regression model that predicts probability of the arrival delay based on the day of the week and origin. So let's do that. And I'll need to be careful to skip the actual model building step. Yes, so I already pre-built, or I should have pre-built this model. I hope. Yes, model 6 is here. So we can skip the model's building step, and let's check that we still have the model. Yes. So now we have the model, and we can use this powerful trick that Bill talked about, where we have built a model on the distributed cluster. And now we are going to score the model using local mode, which is much faster for smaller computations. So to do that, we'll set these parameters, and we'll set the compute context into a local mode. So now we can use this model to do a predictions. So let's do prediction. Takes very quick, very small time, and now we can plot our predictions. There's our predictions. Figure margin too large. Okay, now it worked. So what we predicted is the probability of delay if you're flying from Atlanta airport would be somewhere between Seattle and New York. So I guess that puts us in the middle in terms of our chances of delay. So it's good that we are not in New York. It's bad that we are not in Seattle. But I'm going to come back to Seattle today, so that's better for me, I guess, except for the weather. So what else here? So we have a few minutes more. So another tool that we have in our disposal is a new R tools for Visual Studio. And those are capable of working with your HDInsight cluster as well. So any of you use R tools for Visual Studio? Well, that's a new thing. Oh, 1, 2, 3. Few people already use it. Yeah, so that's a new awesome tooling for R that is available as part of Visual Studio. And you can do similar things that we did in our demo. So the only exception is that Visual Studio instance that you see on the screen is running actually on my laptop, not on the cluster. And that allows me to kind of build my development environment on my laptop and then connect to my remote cluster to push this compute-intensive tasks to it when I need. So this is the way I use it. So this name of the session describes the name of the cluster that I want to connect to. Let's just quickly spin up these things. Again, I specify Spark context as a way to execute things. Very similar script to what we we used to have before. And just to show that it works, so Rex Spark cluster. And finally, we can spin up a machine learning task here. If you go back to the cluster, hopefully we'll see that it works. OK, yeah. So you can see that I was able to launch a kind of scalable machine learning job directly from my laptop using Visual Studio tools for R. So now this job runs in a similar manner as it was running from the R Studio. OK. So now we can proceed to our slide deck. Any questions so far? Yep. So the question when to use RStudio and when to use R tools for Visual Studio. Well, if you have this question, you certainly need to start with R tools for Visual Studio. Well, it depends on if you prefer Visual Studio environment, you'll find it more familiar to work with R in Visual Studio. But RStudio server and RStudio itself is quite a popular tool for R developers. So we support it as well. Yeah.
I would add that
Whatever you compile, you can port it to a Linux platform.
they're both talking to the same interpreter, using the same R language, and returning the same information back, showing you how the interpreter is running, giving you the same graphics. They're essentially identical. What's different are things like keystrokes. And so how many of you remember VI? Anybody ever try and get somebody to stop using VI? You have to amputate their fingers. It's the same with people who use RStudio. They love the quick way that they can use RStudio because they understand how all the keystrokes work. Now, we mimic most of those keystrokes in RTVS. So people can transition very quickly if they want. The place where RTVS makes the most sense is where the desktops are not Linux. They are Windows, number one. But number two, remember we talked about building in Spark and then deploying, say, in SQL Server? One of the great advantages of doing that is you can have SQL guys do data manipulation. And some people will do both. Well, RTVS is one tool. So they can do all their SQL development, data object inspection, play with the database in the very same tool in which they are generating their R scripts to do other things. And since we support embedding R inside of SQL, it's another key thing. You write some R, you get it working. OK, now I want to make that part of a stored procedure for my ops team to deploy. I paste it together in the tool and send it on. So if you're in the mixed and hybrid environments, I think that strongly favors RTVS. If you have very strong Linux teams, people who grew up on Linux and do R on Linux, they're probably going to want to stick with RStudio, but they could shift if you could convince them with sufficient bribery. That help?
Thank you, Bill. Yeah. If you have more R server questions, please fire them away. We have good experts in the room.
To do it now. I was just saying, does RTVS integrate with HDInsight at all?
Does RTVS integrate with HDInsight? Maxim just showed that. There's a couple of different ways to do it. You have to, the most common way is to use PuTTY as a tunnel. There are some other mechanisms to use the SSH keys inside the shell. Your code shows some of that, didn't you?
Yeah.
Yeah, you could flip that back up.
I thought that was all RStudio, RServer.
Oh, sorry. Let me show it again.
They both essentially have to do the same thing. The only advantage RStudio has is you can run RStudio on the head node of the cluster and then use thin client, in other words, web browsers to get at it. And that perhaps expresses one advantage that is distinct from RTVS.
Does this answer your question?
Absolutely.
OK, awesome. Yeah, but just to make sure, you can connect from RTVS to HDInsight cluster, no problem.
And we're supposed to warn you that we love the questions. If you could possibly get to a microphone, that's great. Otherwise, ask an easy question that we can repeat.
Yeah, that's good. Thank you. OK. So a quick tour of the deep learning. Oh, we have more questions. Yeah, go ahead.
Just one quick one. On the RX libraries, you brought in, I went to CRAN, I didn't see them there. How do I pull in those RX
RX libraries. The question is, how do you find the RX libraries? The package is called scalar, and it ships with the product. It isn't open source. It's the commercial secret sauce in the product. So it comes with the distributions. Now you can get it for free on MSDN. You can get the R client, which is free. So there's a number of ways to get those libraries, but we don't share the source code because there's quite a lot of trade secret buried in how we parallelize all that stuff. Does that answer your question?
Thank you.
Okay. More before we move on?
More questions?
Okay, deep learning.
Yeah. So deep learning, that's a deep topic. So we'll only cover very high level just to introduce those of you who are not familiar with it. So deep learning is a new kind of a machine learning algorithm, which is actually not new, which is just a neural network that existed before, with added kind of couple of capabilities to it, with some modifications that run on large volumes of data on a large, deep neural networks. And that two later parts kind of made the difference in the results. For example, in 2012, that's a breakthrough for deep learning networks. ImageNet competition of image recognition found a new winner. And that winner was a deep learning library that overpassed all other previous attempts at image recognition in a significant way. And from that moment on, the whole scientific community kind of latched on deep learning networks and their capabilities because they were showing such a tremendous improvements in our recognition results. And since then, there are multiple achievements that deep learning community have made. One of them is ability to describe a content of an image. So you can imagine a picture that has people in it and fruits, and the algorithm would describe what this picture contains. It would say, hey, this picture contains image and people, or people eating images, and things like that. So quite amazing stuff. And finally, this year, AlphaGo, that's a Google's deep learning network, won a world champion in the game of Go. So the game of Go was considered one of the hardest games due to its combinatorial complexity, much harder than chess, which was previously won by computer as well. And AlphaGo was able to defeat our human counterpart. So I don't know what game we have now where we can still win. I hope there is some game that we're still winning. Okay, maybe that one. So deep learning is a big new area of research. And one of the kind of key elements of the big deep learning is its reliance of the big data sets to get better understanding of the subject, as well as a requirement for the big computational tasks. This is an example of one of the recent, again, image recognition networks called Inception version 3. And this specific deep learning network was designed to reduce the computational complexity of this network. Well, the result was still a network that consists of all of these layers. So on this picture, you can see layers of the deep learning network. Together, these layers contribute to 25 million parameters. And all of these parameters needs to be trained as part of the deep learning training. And although this network was optimized for computational simplicity, it still takes 2 weeks of training time to train this network to recognize these ImageNet images on 8 NVIDIA GPUs. So that's a lot of compute power that you need to employ here to train it. The results are great. You can see on this picture spotted salamander and fire salamander. And if you can recognize those two, well, I'm impressed because I cannot. But this network also can recognize the spotted salamander from fire salamander. I don't even remember which one is the one. Why it's important for our cloud computing and for HDInsight? Well, because in the cloud compute environment, you get ability now to run computers equipped with GPUs that are important for efficiency of the deep learning training, as well as you get natural benefits of the cloud where you can request this compute power on demand. So you don't need to buy hardware to do this training. You can just on demand, when you need to run experiment, request appropriate number of machines with GPUs and run your training. So that's a very convenient way to use cloud compute resources for machine learning tasks. And that's where HDInsight comes into picture. To demonstrate your ability to solve variety of machine learning needs, we decided to bring one of the deep learning libraries into Spark cluster and show how it can interpret with other machine learning tasks that you can do on this Spark cluster using Spark tools or R server. So in this list of deep learning libraries, we chose one that natively supports Spark, deep learning for J, and we tried to run it on the cluster. So apparently that didn't take much effort. You just take this code, build it, and just submit it as a Spark application. So just a very natural set of steps. Let's see if it works. So this is a submit command that submits the already built project.
You might explain it's almost unreadable.
Small, unreadable, okay.
Small and faint.
It's a good point, and it's not working, so maybe.
Leave it small and faint then.
Let's see, we have a few minutes more. Let's give it a chance. So what was the error? Class not found. Okay. To those curious of you, so we are using Spark submit, which is standard Spark command to submit jobs. And we specify parameters that tells Spark to use 620 executors. So that's a number of, that will translate to a number of VMs. And then we just specify what to run. So inside of this sample that I'll explain what it does in a second, we specify what class to run. So basically standard kind of Java things. So let's run it. Seems like something is happening. Let's check that it has created an application. So again, so our previous application that we ran from RTVS has completed, so there is nothing here. But now we can see a new application that just created called mnist. And now it started executing. So while it's running, I can explain what it does. So mnist is like a hello world for deep learning. It performs a simple task of recognizing handwritten characters. So there is a 10 handwritten characters from 0 to 1, from 0 to 9. And it's given a training set from which it's supposed to learn how to recognize the characters. And then it's given a testing set. So in this case, you see results of the test of this training session. So for numbers 5, 0, 4, and 1, it was able to recognize 5 as 5, 93%, and 5 as 3, and 2%. So you can see it's not perfect. There is an error rate here is quite high, but this is just a hello world sample. And on our cluster, let's see if it's still proceeding. Yeah, it's still doing its training. On our cluster, this training should take around a minute. And if you would run this training on a single machine, it would take around 30 minutes. So obviously, it's a great speed up if you run training algorithms on a distributed cluster of machines. We have. OK, while it's running, let's switch back to presentation. And maybe we'll check back on it in a minute or so if it completed. So now that we have talked about R server, Spark, Python machine learning capabilities, and even deep learning libraries, we can put all of these pieces together and summarize what is possible with our scalable machine learning capabilities in Azure. So using classification of the algorithms, and now we have inside that the language matters as well, we can build this table, which basically tells a simple picture of how different capabilities of R server and Spark contribute to a fairly broad and comprehensive offering. So if you're R person, then R server will provide premium experience for any traditional machine learning algorithm you have. The R server community would also be able to provide you with a variety of algorithms of a more rare breed, and that with a variety of specialized algorithms according to our categorization. And similar logic applies to Python and Spark machine learning algorithms in Python. All of the traditional algorithms are implemented in Spark itself, and Python community has a great variety of algorithms implemented for specialized algorithms as well. And finally, you have the ability with the HDInsight as a open source, as a platform based on all of the open source tools to use all of the artifacts, including deep learning libraries, on the cluster to solve your machine learning needs at scale. Okay, so now let's check back on our machine learning algorithm, and it was able to complete, but now accuracy is even 87%. So certainly there is some data scientists here need to go and improve these results, take it as a challenge. But that shows that it works, and we can conclude our session and switch to a Q&A. Bill, am I missing something?
No, I'd only make one additional point. One of the things that you should all bear in mind, especially those of you that are in the infrastructure business, is how you can work with your data science team. One of the questions I meant to ask earlier, and I simply forgot, how many of you are a data scientist? I asked that, right? How many of you are infrastructure people? How many of you have data scientists in your organization? Keep your hands up. Do you have data scientists in your organizations? Keep your hands up. You do. Do you know who they are? You do. Most all of you do. When I asked that question 6 months ago and a year ago, the percentage of hands that would stay up, do you know who your data science teams are? It's not very large. It's because these challenges are pan-organizational. And one of the key points about extending upon what Maximus told you is that not only can we mix and match various stacks of technology for doing the machine learning parts, but Spark, for example, includes SQL components, Spark SQL, that are accessible to R. They're accessible to other languages as well. We still observe that in most of these problem sets, except where we get an already cleaned up data set, the airline data set comes to us pretty clean. If we get a drug interaction database or a text-based database, it's going to be dirty. It's going to be a lot of work to loading and cleaning the data. Anybody ever heard that old rule, 80% of the problem is fixing the data up so you can use it? It seems to be actually worse in data science than it was in data warehousing. So one of the additional capabilities beyond multiple machine learning stacks of multiple languages is new skills can come on board to help with the problem set of getting data in and keep the data scientists focused on what they get paid to do. If they're hard to find and they're expensive talent, your CIO will appreciate bringing other organizations and other talents to bear on these big problems using SQL and other tools that we know about. Again, another reason to consider using RTVS because you have SQL tools sitting in the same tool frame as the R tools or the Python tools. Okay, so with that, Q&A, questions? If you've got something really complicated, jump up and grab a microphone, otherwise we'll just repeat the questions.
Yeah, on the previous slide, you show those algorithm deep learning. You didn't implement R in Python because there's not enough time for those to convert them over.
Sorry, repeat the last part.
The R and the Python.
Yeah, can you use the mic, please? Thank you.
On the previous slide, you have R and Python missing in the deep.
In the deep learning category?
Because of a resource constraint.
Yeah, so that's a great question. So we are focusing here on the scalable machine learning offering, and while there is some simpler libraries that do scalable machine deep learning in R and Python, there was no robust offering that we found in Spark. So that's why there is missing missing category here. But in all kind of, if you're very broad in your definition, what is a deep learning algorithm for R and Python, there are some candidates that you can use in these cells. Yeah.
Before everybody takes off, one last thing I would urge you to do, if you can take a moment to fill out the evaluations, unless you want to give us a bad evaluation, then just send us an email so we can use our delete button. Seriously, we do use those evaluations. We study very carefully what you tell us about what would make it better, what you didn't see, what you liked. And you know, we don't get to come back if we don't get good reviews, so you know, be nice. But do tell us what you think you needed to see. Any other questions from anybody? Yeah, go ahead. Would you mind grabbing a mic? Sure. There are people that are going to watch the recording, so.
Sparkly R is fairly new. How much does that change the codability implications that you've put out there?
Well, Sparkly R is a fairly new thing, so it will, if you're familiar with it and if you're willing to use it, that will probably change the picture. But I cannot answer right now how good it is it doing what it's trying to do? So that would be the answer.
The answer from a products point of view. From a products and positioning point of view, we intend to make it possible for you to use any of the available stacks that present an R interface, and it's a package interface, and therefore it will work with Microsoft R Server. I would caution anyone to ask the question. There are two approaches here. One is to use everything Spark can provide you and be locked to Spark if you believe Spark lives forever, as Maxim does.
Oh, it will.
And my point of view is that there are some cases where the ability to move things from platform to platform is of high value, and that's a choice where you would not want to use Sparkly R. So each tool you use in your arsenal, you evaluate its fit for your probable direction as a company or as a project. But I think Sparkly R is essentially yet another stack that will get good support from the industry, and you will want to use it in Spark from your R applications. And we will not do anything to impede that. We think that kind of openness is critical. Last question in the back?
Yeah. Do you see a significant reduction in the margin of error for using larger data sets?
Do we see a significant reduction in the margin of error for using larger data sets? I'll make a broad marketer's comment on that, and I'm going to ask Maxim, who's far deeper technologically. There is a point of diminishing returns. What we observed at Revolution Analytics as we were working with customers is that when they were working on the more traditional statistical problems, that R was generally the go-to tool, that most of those problems wound up having people working on file sizes in the 50, 100, 150 gigabyte range. And that was plenty. The only place that we saw in traditional R much larger data sets being used were the initial clustering, the initial classification, where you're gonna decide, you know, what model do I build for, you know, this cohort versus this cohort. That cluster needs to eat a little more data. Once you got down into the cohorts, 50 gigabytes generally gave gobs of accuracy, and adding another 200 gigabytes of data didn't really do very much. My suspicion is, and I believe Maxim would back me up, in the machine learning space, however, tack another couple of zeros on those numbers. So we do, in certain formats, either machine learning around, K-means is the beginnings of machine learning. The deep learning that Maxim is talking about, you're now talking about things that are going to consume far more amounts of data before they reach acceptable accuracy levels. That's why Spark is so damned important to us. Did you have
it certainly depends on the algorithm. Deep learning is a good example. It only exists and is because it found a way to use large volumes of data to achieve better margins of errors. So that's it dependent on the algorithm, and more nonlinear algorithm and more complex you go, probably there's more opportunity to extract value.
I probably don't need the microphone, but as far as version of R that's supported, so with R server, I don't know, the current one, I think it was 3.2.2 or something, is there an expected cadence with which there will be any updates made to that version that's supported?
That's a very good question. We've discussed that a lot internally. It is in our benefit to remain as up-to-date as possible, but at the same time, not to force people to jump when they don't want to. We've been able to remain current within about 60 days, roughly. Occasionally there's something that slows us down, and occasionally we're busy doing something, and it might take a little longer, a little shorter. We're also looking at some broader questions of, is forcing people to support the latest rev of R really a good answer? It's never been a good answer. The R community got away with it do we, as we move out into production systems, really want to continue that philosophy? That's essentially under discussion. You drop me an email, I'll be happy to keep you up to date on how we discuss that. It's BILLJAC@Microsoft. That's a great question. Yes?
I have terabyte of data, and right now I see a solution of SQL data warehouse and all. And how does that compare to Spot on? With it to Spot on, you mean some advantage over data warehouse and all?
Yeah, the question was, he has SQL Data Warehouse and R. How would that compare to Spark and R? Would that be the question? You want to take your meeting?
That's a reasonable question. I think that's an interesting combination. And in terms of our server capabilities, I think it would actually be better served by SQL Data Warehouse and R because it's a parallel solution and it runs kind of natively on the platform. The moment you want to get out of the R confines, then you probably want to consider Spark as a backend. Yeah.
There is not an implementation of our server for SQL Data Warehouse yet. The R server will work with SQL Data Warehouse, but we don't yet have it running inside that data warehousing product. When we get there, that will bring SQL ease of use and massive parallelism together, like we have in Teradata. Today, though, you would be using it in the context of of an R engine running in a server talking to a database, typically via ODBC, JDBC. Unless you know of a secret project I don't know of.
No, I don't know. So the question was about the future direction. When you have those two capabilities, which I think is logical to expect will be available.
We see a rapid growth in SQL-based big data analytics simply because there's so many people in the world that are very, very comfortable with SQL, but are less so with, say, Spark, MapReduce, and languages like Python, Java, Julia, that kind of thing. So again, the question people want to ask is, gee, what should I use? Well, you should probably use the thing you already know if it'll do the job. You know.
Worried that if you have tons of data, way more than like petabytes, and then obviously you cannot do it on SQL Data Warehouse.
I'll tell you that SQL Data Warehouse, if and when we implement our server in SQL Data Warehouse, and we have contemplated doing that, there are discussions and investigations underway. If and when we do that, that extends an in-database capability that has historical analogs. I came from Pivotal and before that Netezza, which both do massively parallel, shared nothing architectures, which is what SQL Data Warehouse is based upon. And there aren't great examples out there of moving into the petabyte range. We don't yet know whether it can be done, is really what I'm telling you. We saw in those other databases terabyte, 10 terabyte kinds of applications. I don't know of cases where, say, like a Postgres with the MATLAB libraries have been pushed up into the petabyte range. Now, again, petabyte in the store doesn't mean you're running a petabyte in the algorithm. So the question is really, how much data are you feeding the algorithm to achieve the levels of accuracy that we were just discussing? Yep. More questions?
I just have one more.
Yeah, go ahead.
About the R server with Azure SQL, is that an if or a when, or can you say?
That is as well on the roadmap without a committed date. So you'll have to watch this space. But as is alluding here, I love massively parallel shared nothing machines because they give you SQL ease of use and massive parallelism. Whether we'll do that anytime soon, that depends on some other questions. Right now, the enthusiasm for Spark is exceedingly strong. So, more questions? Well, with that, thank you very much for your attention.
Thank you very much.